What's the speed of light? 300 meters? 300 meters, just think about it. In 1 second it goes 300 meters. 300 meters is kind of small. It's not really that big. 300 meters, like this one is 1 meter. And in 1 second it goes 300 of these. No, light is way too fast. Okay? So you're kind of right. So we represent the speed of light by the letter C. Speed of light in physics is usually represented with the letter C. Okay? And what is the value of C? It is 3 multiplied by 10 to the power 8 meters per second. That's the speed of light. It goes pretty fast. Okay? It's kind of 300 million meters per second. 300 million meters per second. That's the speed of light. Right? So it's pretty fast. Now there was a big scientist, his name was Einstein, and he said that when something is going with the speed of light or something near to the speed of light, okay, then we say that its speed is relativistic speed. Okay? Relativistic speed. So what is a relativistic speed?
Time.
Time is a relativistic speed? No. What is a relativistic speed? So I'm running from here to here. Okay. I'm running at a relativistic speed or not? Huh? No, I'm running too slow. The speed of light is way too fast, right? So I'm not running at a relativistic speed, right? Okay? You understand? But if I would be running at 2 into 10 to the power 8 meters per second like a Superman or a Flash, right? A Flash runs that fast, right? So if I'm running at this much speed, like 200 million meters per second, if I run with that kind of speed, then would you say that my speed is relativistic speed?
No.
Yes. That speed would be relativistic speed because it's 10 to the power 8. It's comparable, right? You understand? You get it? So 200 million meters per second would be known as the relativistic speed. Okay? But 5 kilometers per hour?
No.
That's not a relativistic speed. You understand now? Now, if Mr. Einstein said that if something is moving at a relativistic speed, its mass changes, right? It becomes fatter. It becomes more massive, right? You understand? So, for example, what's your mass? How many kgs?
About my weight,
Yeah,
it's like maybe 60.
60 kgs.
Yeah.
Really? Okay. Let's say you're 60 kgs. So what if you start running at a relativistic speed? Is your mass going to be same 60 kgs or is it going to increase? Yeah, it's become, you're going to become fat. Oh, like this. Okay, like a Hulk. Right? So once your speed starts increasing, you start gaining mass. Okay? And if you start running that fast, is time going to become slower for you? Yes, you'd see things happening faster. So if you are running that fast and I'm drinking a tea, for normally I'm drinking tea like this. This is the tea I'm drinking, okay? But if you're running like a relativistic speed, how would I be drinking tea? Like slow motion, right? The time will become slower for you. Right? But when? When you are running at a relativistic speed. Okay, so the time, the mass, the length, it depends on how fast you are moving. If you are moving faster, the time becomes slower. If you start moving faster, you become fatter. Okay? The mass does not remain the same. The time does not remain the same. It depends on your speed. Okay? But what about the charge? Does it also depend on your speed?
No.
No. Okay? So when something does not vary on the basis of your speed, we say that it is relativistically invariant. Do you understand that? So the next property, so is mass relativistically invariant?
No.
No. Mass changes. Is time relativistically invariant?
No.
Is charge relativistically invariant?
Yes.
Yes. Okay. So the next property is that of the charge. So charge is relativistically invariant. Understood? This is relativistically invariant. These are the properties of charges. Okay? Got it? Okay. Now, what was the next topic? I did. It was conductors and insulators, right? Conductors and insulators. Conductors and insulators. Insulators. Okay. Conductors and insulators. Now, is this bottle a conductor or is it an insulator?
Insulator?
Is this a conductor or insulator?
Maybe insulator?
It's an insulator. How would you know that whether something is conductor or insulator? Okay. What can we do is that let's try to figure out whether this is a conductor or whether this is an insulator. Okay? What we do, we put it inside and I get a shock. What it means? It means it's a conductor. Okay? And if I don't get a shock, it's an insulator. So a conductor conducts electricity. Electricity goes in it. If it's a conductor. If it's an insulator, electricity doesn't flow in it. A conductor is the metal usually, like wires, like iron, like aluminium, usually, right? But they are not metals like graphite. It's also a very good conductor. Okay? There are a lot of things which are conductor and there are a lot of things which are insulators, right? Like this table. Is it a conductor or insulator? Insulator. Water. Is it a conductor or insulator?
Conductor.
Water is a conductor? Who says that water is a conductor? How many? Conductor? Conductor? Sure? So a pure water is an insulator. If you have a pure water, okay, 100% pure, only H2O, then it's a insulator. It doesn't conduct electricity. But what happens is that when we put some salt in it, some sodium chloride in it becomes a conductor, right? Because they are ions, you know, you remember in the last lesson we talked about cations and anions? Do you remember the formula Na plus and Cl minus? Right? It becomes a cation, it becomes an anion. So it has a charge, right? It has another charge. If we put it inside water and we just mix it, there are lots of positive and negative charges in it, right? And it's free to move, it can float around, right? And when we are going to put electricity in it, we are going to get shocked and we're going to die. So usually the water, the kind of water that you drink, is it a pure water or not?
Non-pure.
It has a lot of sodium chloride, magnesium chloride, a lot of ions in it, right? That's why if you're going to swim in a pool and I'm going to put electricity in it, you're going to die. So normally, the kind of water that we put in a battery that's known as that's known as distilled water. Distilled water is a pure water. It's just H2O. That's kind of insulated. It's not a conductor, right? So what happens when we put NaCl, salt in it? It becomes a conductor. Why? Because there are moving charges in it. Okay? These are known as the charge carriers. Okay? What is the sodium positive ions and chloride negative ions? What do we call it?
Charge carrier.
Charge carriers, right? Charge carriers, right? Carriers. So if something has a charge carrier in it, something which can carry charge inside a material, then that is a conductor. Okay? And then we have some kind of things which do not have charge carriers. The insulators. Right? You understand? So if we are talking about air, okay, is air conductor or insulator? It's usually insulator. But you know, have you ever seen kind of lightning in the sky?
Yes.
So electricity can flow through the air. But for that we have to have very high voltage. Extremely high voltage. Okay? So if there is an extremely high voltage, then the electricity can flow in the air as well. Right? So the thing is, whether something is conductor or insulator. So for example, rubber. The rubber. Is it a conductor or insulator?
Insulator.
But if we are going to put it at a very high temperature and I melt it, okay? I melt it. We have a molten rubber. Then it's going to conduct electricity. Okay? We have the same rubber, but it's at a very high temperature and it's molten. Then it can conduct the electricity. Understand? So when we are talking about a conductor or an insulator, what we are actually talking about, do we have the capacity of charge to flow in it or not? You understand? So somehow we can put or we can free some charges inside of it so that they can flow. Then it becomes a conductor. The same thing which was an insulator, it now becomes a conductor. How? If it has free charges. Right? Now water, pure water, it has no free charges. Okay? So it is an insulator. The electricity cannot flow. But when I put some salt in it, it gets floating ions all around, right? Okay? So all the ions are going like this, okay? A lot of ions are swimming inside the water, right? So when all the ions are swimming inside the water, if we are going to put electricity in it, okay, the potential difference across it, then these floating ions can move from here to there. Then water becomes conductor. Okay, you understand now? So when we are talking about the metals like this one, what can we say? That these have free electrons in it. Okay? The atoms are joined together, are bonded together in such a manner that we find a little bit of free electrons in it. Okay? And when we see that there are free electrons in it, they can flow. And it becomes a conductor. Okay? Wood is an insulator because we don't have free electrons in it. Okay? So what is a conductor? Conductor is something that can conduct electricity. Okay? Electricity due to the presence of free electrons in it. Right? What are insulators? It can not conduct electricity. It cannot conduct electricity due to absence of free electrons in it. Okay. Tell me, is this wood a conductor or an insulator?
Insulator.
Insulator, right? Does it have electrons?
Yes. No. Yes.
Does it have electrons or it does not have electrons?
Has electron.
It has?
Yes.
How many of you say that it has electrons? Yeah, it has. It has atoms. All the atoms have electrons, right? But the problem is all the electrons are bound. They are not free to move. Okay? They cannot flow. Right? So just imagine that in Al-Khor, all the boys and all the girls are just put in the room and the door of the room is locked. They're not allowed to go out. They have to stay in the home. Okay? So they want to go out. They see that, oh, I want to go out, I want to swim, I want to do all the things in my life. But the parents are not going to allow it. So what's happening? They are boys and girls, but they are not allowed to move out. All of them are stuck in their houses, right? The parents are going to give them a good thrashing if they want to come out. Huh? Okay? So if you want to go out of the home, your father is going to come and hold you and goes, come on, come back to the home. Okay, you're not allowed to go out. So that's kind of bound people. You're bound by your parents. You're not allowed to go out, right? Okay, so these kind of electrons are present in this wood. Electrons are there. But the parents of electron, they are kind of putting them down in the rooms. You're not allowed to go out, right? So these are the bound electrons. And they cannot flow, right? But in the metals, okay, in the metals, the electrons are kind of free. Okay? These are vagabonds, they can go anywhere, they are free. Right? But there are still few electrons which cannot move, and there are few electrons which can move. So when we are talking about the conductors, they have free electrons as well as bound electrons. Okay?
Can conductors become insulators?
Conductors, yes, they can become insulators. Right? If we are going to put them in such a situation where the electrons get bound. Right? For example, let's talk about graphite. Okay? Graphite is made up of carbon. Okay? And it's a very good conductor. Okay? Graphites are extremely good conductor of electricity. Okay? So the graphites are usually used in conducting materials, right? But it's pure carbon. Graphite is pure carbon. But just imagine if you are going to put graphite in huge temperature and pressure, do you know what it becomes?
Diamond.
It becomes diamond. Okay? The graphite, which is a good conductor, becomes diamond. Now, is diamond a good conductor or a bad conductor?
Bad.
It's a bad conductor. So do you see a good conductor converting into bad conductor? So why? Because the structure, the way the carbon atoms are linked with one another, it changes, and it changes in such a manner that all the electrons which are free to move inside the graphite, now they get stuck between atoms. Now they are not allowed to flow, they are not allowed to move. Got it? So, does that answer your question?
Yes.
Okay? So, now you understand the conductors and insulators. Okay? So when we want to understand how to give charge to a body, okay? So this is something that we have. Okay? This is a rubber. And I want to give some charge to this body. Right? I want to make it charged. Now there's a question in front of me. How to put charge in it? That's a big question. I want to charge something. Now, when you want to charge something, you have to understand how to give it some charge. Before we devise a mechanism, we try to find out a process to give charge to this body, we need to understand what kind of body is it. Is it a conductor or is it an insulator?
Conductor.
Right? This is not a conductor right now.
It could be because it has a.
Okay? So the first example that we took today was that of a glass rod. And that was rubbed with a silk. Now both of them are insulators. Okay? Now when we have an insulator and we want to charge it, we can do it by rubbing, by friction. Okay? What happens when we rub one body to another? When we rub this body to this body, first of all it becomes hot. The second thing is that the atoms on this surface and the atoms on my hand, they are kind of rubbing against each other. So do you think that a few of the electrons are going to leave one surface and are going to go to the other surface, right? So there's going to be one body which is going to lose electrons and another body which is going to gain electrons. The electrons are getting transferred from one body to another body because of the friction. Got it? And this transfer of electron can be used to charge an insulating body. So if you have an insulator, you can charge it by rubbing. And that is known as the frictional electricity. What do we call it? Frictional electricity. And there's a very special term for it. We call it triboelectricity. Triboelectricity. Okay? So what is a triboelectricity? Triboelectricity is a charging of a body, of an insulating body, by rubbing against each other, and that is the friction. Okay? Because of the friction. You got it? You understand? Okay. You have you taken the note of this one? Go ahead, write it down.